Hello again, everyone. Welcome to today's lesson. This topic is called the inverse of a function. All right. Now, you've actually done some things with inverses before. For example, you know how to take the sine of an angle, um, but you also know how to use the function called the inverse sine of a ratio to get back an angle. If you have a function f of x, if it's written in function notation, then the inverse is written using this notation, f, and then what looks like an exponent of -1 is not really an exponent of -1. Just like for inverse sine, that doesn't mean 1 over sine, does it? It doesn't mean an exponent of -1. It actually does mean the inverse, okay? So there's a function, and it has an inverse, f inverse of x. One thing about a function and its inverse, what does an inverse really mean? Well, it's kind of the opposite of the original function. It undoes whatever a function does, okay? All a function does is take a number and do something with it. It turns it into something. Well, the inverse kind of undoes that. Let me come down here. I'm going to get some blank space here. Okay, this is just some blank paper. Now, you can write this down if you like, but I want to show you how a function and its inverse are related. Let's suppose I drew a box here. Okay, so there's a box. All right. Now, what in the world is inside that box? Well, you know what's inside of it? A function, f of x. Okay. Now, I don't know what the function is, right? It's no doubt involving numbers and mathematical symbols and things like that. But all a function does is it takes a number, it inputs a number, and then it outputs a number. So the input, let's suppose we input something like, I don't know, like a 3. So on one side, you put the 3 in. There's a little hole on the other side. See, a little slot. And here's a little slot on the outside. This is where we get back our output. All right, so input, output. So what if you put in a 3 into that function and it did something, and then what if it spit back a 7? Okay, so you put in a 3, and it did something to it, and you got back a 7. Well, remember the number that you put in, which in our case is 3, that's also something called the domain, isn't it? That's one of the numbers in the domain. 3 is in your domain. That's one of the x values, what you put in. So that's your domain. And remember, the number you get back is like your range, isn't it? That's like a y value. So you put in an x, you get out a y. You put in a domain value, you get back a range value. Okay, well, what if there was another magical box right here? Oops. Okay, I'm kind of like halfway down the page there. Here's another box. Okay, another magical box. And this box, though, is not a function. This is the inverse of the function. Okay? And again, we don't know what it is, but all I know is that it undoes what the box up above does. It undoes that whatever the function does to a number. So in other words, it has an input as well, and it has an output as well. But remember, if I put in a 7 this time, remember it undoes what the original function does. So if I put in a 7, then it will spit back a 3 because it undoes what the original function does. Now, there's a few important things I want to point out here. Notice that in our original function, we put in an x value of 3 and we got back a y value of 7. Well, that means the point 3 comma 7, that would be on the graph of f of x. If you drew the graph of f of x, 3 and 7 is there. But look at the inverse. You put in a 7, that was the x value this time, and you got back a 3, that was your y value, that was your range. Well, that means that the point 7 comma 3, that must be on the inverse. All right. Now, that's a really important relationship there between a function and its inverse. In fact, if I gave you the graph of a function, you could easily draw the graph of the inverse just by taking the points that are on the graph and switching the coordinates around. You don't even need to know what the function is. Isn't that amazing? But there's something else here as well, something else that's important. Notice that the domain of the function was 3, That was your original function. Do you notice that turned into the range of your inverse? Look at that. So the domain of the function is equal to the range of the inverse. And the range of your original function, which was a 7, suddenly turned into the domain of your inverse. Now that's another important property there as well. All right, that's very important. Let's come up here above, and there's a few other things I want to go through, but you remember that very simple little diagram about how a function and its inverse are related to each other. Here's another way I like to think of it. Look, the x's for your function turned into the y's of the inverse. The x's turned into the y's, and the y's of your function turned into the x's. Oops, turned into the x's of your inverse. So another way to think of it is the x's become y's. The x's become y's, but also the y's become x's. And that's a simple way to think of it. But between a function and its inverse, that's exactly what it's not squared. Becomes x's. That's the relationship. The x's become y's and the y's become x's. The domain becomes the range and the range becomes the domain. And the points just get switched around, the coordinates. Now, that's kind of what this is saying here. The functions f of x and g of x are called inverse functions only if both of the following statements are true. Here's a little test, you see, that you can use to determine if two given functions are inverses or not. If you take the composition g of f of x, and if you get back exactly x all the time, and the second part to that test is if you take the composite function f of g of x, and again you get back x, then those two functions must be inverses of each other. All right? Because think about it, they undo each other. One undoes what the other one does. So obviously you're going to get back what you started with. Down here in this simple diagram, we started with a 3, we put it into our function, we got something back, but when you take that something and put it into your inverse, you get back the 3, which is exactly what you started with. All right? So here's example number 12 on page 23. You could have a question like this on a quiz or on a test, so it's very important to make sure you understand how to do these. We have two functions given. Here's the function f of x, and here's the function g of x. All right, notice they're different. That's fine. Show that f of x and g of x are inverses of each other. Now, according to that little box we just looked at up here, there's two parts to this test. You have to take the composite function f of g of x, and hopefully you get back just x. That's what you should end up with. But then you take the composite function g of f of x, and the same thing should happen. So watch this. Here's my first test. F of g of x is equal to f of. Now, the g of x is 2x plus 1. So remember what that means. I look at my function f, and wherever I see an x, which is right there, I replace that with 2x plus 1. So this is going to become bracket 2x plus 1. That takes the place of the x. And then minus 1. And then divide by 2. Now, you just simplify that as much as you can, all right? So you would remove the brackets first. They just vanish. There's nothing in front. So you're just going to have 2x plus 1 minus 1 divided by 2. And now the 1's cancel, so you have just 2x divided by 2. And those 2's cancel because they're factors. So look at that. Voila, you got back just x. Perfect. You're halfway there. The second step to this test would be to work out g of f of x. All right. So in that case now, you're working out g of, and f of x is x minus 1 over 2. All right. So you're going to put that f into the function g right here. So here's what you've got. 2, and then a big set of brackets with x minus 1 over 2 in there, and then plus 1. And now you simplify this as much as you can. Notice that the 2's right here, right off the bat, they can cancel. Because this 2 is in the numerator, and this 2 is in the denominator. They're both factors, so they cancel out. So all you're left with is x minus 1 plus 1. Now remove your brackets, and you have x minus 1 plus 1, and they cancel, and voila, Now you have just x. All right. So what's the conclusion? Here's your conclusion. Since f of g of x is equal to, they're both equal to x. You see, they both equal the same thing. Is equal to f of g of x, or g of f of x, is equal to x. Since both of that happened, then f of x and g of x are inverses. And that could be a question on a test for you. All right, so make sure you know how to do that. In this little box right here, this is still on page 23, they're telling you exactly what our little diagram below explained to us. Look, the range of the function is always the domain of the inverse. And the domain of the function is always the range of the inverse. We saw that down here from that very simple little diagram. For the graphs of f of x and f inverse of x, for every point a, b on the graph of the function, there's a point b, comma, a on the graph of the inverse. The coordinates just switch around. We saw that down there too, didn't we? We saw all of that. Number 2 is very simple, very straightforward. I better hurry up because I'm running out of time. If you know that f of 2 is equal to 3, so in other words, there's a magic function f. When you put in a 2, you get back a 3. Well, what if you took the inverse and put in a 3? Well, remember what the inverse does. It undoes what the original function f does. So it's not surprising, kind of just like that diagram down there, that you would get back a 2. All right? It undoes what the original function does. Now look at b. You're taking the constant function f of f inverse of x. Remember, if the inverse undoes what the original function does. If you took the composite function, just like that test we did a moment ago, if you take the composite function of any function f and its inverse, they undo with each other. They undo what the other one does. So it's almost like they cancel out. In fact, they kind of do cancel out. All you're going to get back is a 3. And even if you take the inverse first, the composite function f inverse of f of 2, ladies and gentlemen, is just going to be a 2. That's it. All right? Now, there's one other thing I want to do in this video because this is very short, very sweet, very easy. Notice that it says at the very top, we're on page 24 now, that not all functions have an inverse, and that's true. Only certain types of functions have an inverse. It has an inverse only if the function is what we call a one-to-one function. It's also called an onto function, if you want to know another name for it. So that means there's exactly one y value for each x value, and there's one x value for each y value. So that's kind of a stricter condition than just being a function. It has to be a one-to-one function, right? So you can determine if a function has an inverse by using something called the horizontal line test. All right, something like the vertical line test for a function, but this is called the horizontal line test for the existence of an inverse. And here's how it works, the horizontal line test. If the graph of y equals f of x is such that no horizontal line intersects the graph at more than one point, then the function is one-to-one and it does have an inverse. Now that's important, okay? It's kind of like the vertical line test switched on its side. So, example number 3, this will take us about 30 seconds. Use the horizontal line test to determine if the function below, or functions below, have inverses. Well, here's A. It's a parabola opening upward. Now I can clearly see it's a function because it passes the vertical line test. There's arrows on the end of those curves, by the way. But does it have an inverse? Well, if you were to draw a horizontal line, if you could draw a horizontal line anywhere that hits that graph more than once, ooh, and this one does, by golly, look at that. So this function does not have an inverse. Now I've seen textbooks that kind of would argue that point, but I'll play their game here as well. So this function does not have an inverse. All right? Well, we're going to change that a little bit later anyway. Now, if you look at the next part, b, okay, well, here's another function, and that sure looks like, well, it's definitely a function. It passes the vertical line test, and it passes the horizontal line test, so I'm out of time.